Okay, good example of a relatively modern genset. It's a dedicated genset. This particular one runs this vertical hollow shaft and then 4 submersibles off of it. So this is probably a pretty typical area. It's Rita Blanca service. You can't get electricity out there. You've got natural gas. You used to have V8s on each of these wells. The water is declined to where you can have a submersible on those. You can put a genset on here that'll generate about 200 horsepower worth of load and power all of your pumping plants from one central location. And that's really the fit of the genset. So a scenario for on-site electricity generation. There's a couple of parameters because I don't want to talk anybody into a genset that shouldn't have a genset. But if it's a good fit for you, it's a good solution in those scenarios. So if there is limited capacity of existing electricity infrastructure or no horizon that electricity can come to you, or if the power company says we just can't sell any more power and electricity is not an option, look at a genset. If you currently have natural gas infrastructure, and if this is all now coupled with reduced water and power requirements at the wells, you can get a potential for lower energy costs compared sometimes to grid power, sometimes compared to internal combustion as well, because you get to centralize some of your production because of the genset. The trade-off is you're now your own utility on one more front. You're your water company and your power company. You're taking this essentially all into your own hands. And I tease, I was on a panel last week for a bunch of investors, trying to give them a perspective of what an investor needs to know about a farmer. And you go through a farmer, you realize part of being a farmer is that you like being an electrician and a plumber and an operator and a mechanic and the accountant and the foreman and the boss. All of the things. But what I realized is as farmers, kind of like a lot of those trades we mentioned, we can read and write, but we don't necessarily like to. When you start getting into some of these things, this is well within your wheelhouse as a farmer. You're already skilled on how to do all these things. It's not like asking you to be a paralegal or a lawyer. I think that's why gensets work in this area. It's stacking something else, a different application on things that you already have a great acumen for. So if we look at some typical pumping plant energy costs, look at our fuel sources here. So natural gas, gasoline, diesel, propane, electricity. This is a pretty good breakdown. Again, these are stagnant numbers, more or less, depending on where you're at in the country or what time of the year it is. But natural gas, 1 MCF, basically 1 unit. You got 1 million BTUs per unit, $4 per MCF. Relates to $4 per million BTUs. You go through the same math on gasoline, much less per unit, something like $20 per million BTU. Diesel, a little cheaper because you've got more BTUs per unit gallon. You get to propane, it starts to get cost prohibitive. Electricity, kind of in line. Okay, you see natural gas, however, is a wide winner here. This is why we use natural gas. Not because of the efficiency, but because you can get the media very cheaply. You can buy cheap natural gas. If this was $12 a unit like you saw in around 2008, it gets a little different. You have electricity spikes and you're paying more than 7 cents per kilowatt hour, probably like you are now. Or if you do like what some of the farms I've got out west where this is 23 cents per kilowatt hour, everything starts to change. Okay? One thing that's not going to change is if you're pumping from a deep well in this current world, diesel doesn't work for you. Like, we're not going back to diesel. You can't make it happen. Gasoline is, of course, even worse. When you convert that through to water and look for dollars per acre inch, this is how it starts to stack out. And electricity, because of its efficiency, jumps almost all the way to the top. And in some years, electricity is going to be cheaper than natural gas. One nice thing if we want to look about electricity is that it's typically more stable on the market. Natural gas has been pretty stable as of late, which is great, but it does historically fluctuate some.
It's acting up in the winter times where it makes it tough to decide whether it's free water or not.
Yeah, that's right. I mean, electricity, you've got some demand charges if you're buying that off grid. It's hard to say, hey, do I pull the trigger and start this well for a week in February or March, or just the same if you got to buy natural gas and you're competing for people that are heating their homes with it. Now it's very expensive. Yep, all those are factors that weigh in. If you want to know why we don't use propane and gasoline for our pumping systems, those are the ones that are way out of line there. You can't afford it. So we'll go through some pumping plant energy costs. This was a gen set that I was running for a test well. Who's running a 600 horsepower motor in here these days? The reason I put that up there is this is same principles that apply whether you're pumping 5 horsepower or 5,000 horsepower. It's all the same. Natural gas price, again, like I mentioned, there's some volatility, but generally we've had a nice run of stability. Electricity, typically very flat line. Who knows what this spike was? Who can remember this action in 2021? This is just a good indicator of what could play with those decisions you're talking about. Yeah, remember when Texas went under an ice storm and completely froze out, and you had everybody in Dallas and Austin, and the energy price went through the roof. The reason I put this up here is you get to insulate if you generate on site. You go back to some of these stable, lower costs, generate, and you're not subjected to the demand charges, not subjected to the ice storms. Same stuff, different numbers. So this is an energy bill for the center that we looked at. Some things that you're going to compare to, because in order to see if the gen set is useful for you, you need to see what your comparable operating costs would be if you had power. My opinion is if you can get grid power, just go ahead and get grid power. Gen set's not really for you. You may disagree with that, but there's a lot of heartache that comes with running this gen set that you can avoid if you're already going to go to electricity to just get onto the grid typically. Yeah, these are obviously, this example's a little dated, but the principles are the same here. In this case, the average electricity rate, and it's important to point this out to you. You've got to add up all of the customer charges, the energy charges, whatever this demand charge is or credit is. Add that up until you get to your actual number. In this case, for this example, it's 6.3 cents per kilowatt hour. Pretty cheap power then. The electrical generation is what we're going to compare back to that. So remember that first gen set we put on, we went through, evaluated it by testing natural gas, took voltmeters out to measure the volt and amps, measured the power factor on each one of the runs, and added it up to see if he could generate on current delivery of natural gas for anywhere in the ballpark of what he could buy power for. And this was the spreadsheet that we worked up on it, and came up with a cost per kilowatt hour of 8 cents, what he could generate with using $5.50 natural gas. This is the math that we had to go through to get there, but the shortcut, of course, and this is the real take-home for all of this, is remembering these numbers here. Out of the whole thing with the gen sets, if you think you're going to dip your toe into gen sets, these are the numbers that you need to use to compare whether it makes sense for you. So you take your dollars per MCF of natural gas times this multiplication factor, which is basically the summary of all of these things that we saw in the field, of 0.015 as a multiplier. That's going to give you the dollars per kilowatt hour that you can produce electricity for. So in this case, if you got $3 natural gas times 0.015, you can produce electricity for 4.5 cents per kilowatt hour. The reason I'm saying this is if you're going to compare to the grid, this is your shortcut to answer whether gen sets are even for you. And you might sense I'm being maybe a little negative on gen sets. I'm not negative on gen sets per se, but I am negative if you have the mind to say I'm going to do gen sets to beat grid power. That trade-off, that cost to benefit ratio just isn't there. If you've got a bunch of natural gas wells, you've got natural gas on the place, and now you need to run submersibles, this might be a great fit for you, but you end up taking on some of your own headache. You can't really farm that out to somebody else. This is how you can tell whether it makes sense to do this or not. General setup cost, 3-phase power line. You're going to be in the mid $60,000 per mile to run it, and about $14,000 per drop. That's real money, real money. Your gen set's not going to be free though if you do it right. You're probably going to be on a 150 kilowatt gen set, so something like a 200 horse unit. New at 65K, reman at 55K. You're going to have some real money in that too. I wouldn't highly recommend a slap together gen set. Typically you're going to have more problems than not. Retrofitting a 454 with a gen set to power your operation is probably a little bit pound foolish. It can be done though. So sizing this gen set is going to be critical. Remember, you become a utility now, so you need to have a sense of what all of your loads are. Then you need to build your infrastructure out to match those electrical loads. And it's not complicated, but you can't really guess on this because typically with the gen set application, you're going to start fine tuning where you are going to end up with a load, and you don't have the abundance of the grid that would be carrying all of your neighbors' loads to help you. So you have to start paying attention to things like, what's my line sizing? What's my peak load when it's hot outside? What about my inrush current? Do I have to pay attention on how I start my motors or my wells? All of those things become really critical. The other thing you have to pay attention to is what your power factor is. I think the easiest way to understand power factor is it's the efficiency of the power that you deliver with 3-phase. 3-phase essentially comes in 3 different waves, and the overlap of them, if you don't get it lined up right, you miss a little bit of the power that it could be creating. Most everybody's going to claim, oh, we've got unity power, there's no loss with the power factor. My experience is that with gen sets, 0.8 is what's on the label. Most of them will outperform that, something like 0.87 to 0.9. It's really good power. I mean, don't get me wrong, grid power often is off by a factor more than that, but because this is a bit of a D-rate, every bit of power factor that's less than 1 is actually less power that you can deliver to your wells. So it's something you've got to be mindful of. Also add to it, because of where we bump and what time of the year, you've got to use some D-rating considerations. If a motor is rated at 200 horsepower, that's not going to be 200 horsepower at 115 degrees in the summer. And it's not going to be rated at 200 horsepower, 115 degrees in the summer, running 24/7 like you're going to run the gen set. Most of those ratings are something that I would consider for a more reasonable but less likely scenario where you're going to be able to run it for a little bit, ideal conditions, turn it off for a little bit. We obviously don't irrigate like that. Because you've got to be an electrician, you also need to have a little bit of electrical engineering understanding to see why this makes sense. Also to completely talk yourself out of single-phase power doing just about anything you can with 3-phase. So the take-home points here is that it's generated by a magnetic field. So what that generator is on the back of the motor is essentially an electric motor being spun in reverse. Instead of sending power to it to force it to spin and do work, you're forcing work to it and causing that magnetic field to generate electricity, and now you're taking that electricity out to somewhere else. Okay, so any of the principles that you have on an electric motor work exactly with a gen set, only in reverse direction. And I think that's helpful to conceptualize what you're doing with the gen set. At least it's helpful for me. Most all that we're going to do is going to be AC current, so alternating current. Because of that, though, you do have to pay attention to your cycle and frequency. Hertz is the number that we use for frequency. You guys have gotten familiar with variable frequency drives, so you understand what hertz are. but the hertz is how many times that current goes back and forth in a second. You do it in 60 times in a second. That's our standard in America. Most of the motors you get are going to respond best to operating at 60 hertz frequency. If you start alternating the hertz, that's a little what Carlisle was saying. You start manipulating the frequency, you really can start manipulating the power and the way the motor operates as well. But I wouldn't do that with your gen set. I would do that rather with a controller like a drive. The reason I make the point about three-phase power is you get to clip a major coupon in the efficiency of a three-phase motor compared to a single phase. So a single phase basically would say every time it makes a loop, it's going to hit a magnetic field that's going to charge it again, comes around 360 degrees, hits another magnetic field, but it kind of lopes. Okay, you can break that in segments, and that's what the phases would be. And you can go all the way to 12 phase or way on out where it's almost pulsing every degree if you wanted to. But the cleanest way that clips you the biggest coupon, and why the industry has settled on it, is three-phase power, which gives you a square root of 3 efficiency benefit. It's a big, big deal. Big single-phase motors just don't fit this application because you have essentially 75% more power to have to drive it. Like I mentioned, the power factor comes into play here. It has to do with these cycles where this is phase 1, say, phase 2, which is off, and then phase 3, which is off. So you're taking this 360 degrees, and basically a peak is at every 120 degrees all the way through, which basically means that one side's getting driven while the other is making its way through the system. No quiz on this. This is major. Primarily, this is just so that you have an understanding of what you're trying to do with generating the power. Because on one side of the gen set, you're going to generate the power, but on the other side, you need to be using that power and doing all the work that you really get paid for.
That generator has to be internally wound, doesn't it?
Internally wound?
Yes.
You know, I've not seen one that's externally wound, so I'd say yeah.
Okay.
Yeah.
I know it takes, like, if you got a 50 horse motor or a 50 horse pump, it takes twice the KW to start in if it's not internally wound.
We'll talk about that, because that inrush current is a big, big, big piece of this.
Yeah.
Yeah, so most of these would be inverter duty, which is what you're referring to. Yep, great point. And I would say not just the generators, but oftentimes the stuff down the stream are going to need to be of that type of construction as well. So this would be an example of the gen set outputs. This is a digital screen, but typically this is going to be your control panel. Really pretty simple to understand. Telling you your voltage, 481 volts. Most gen sets are going to have a very robust regulator on it because you have to control for this voltage. And so the governor on a diesel gen set is going to be very, very strict. It's hard to defeat those governors. And you don't really want to defeat those governors because the system works together. So the output here is going to show 480 volts, 212 amps at 60 hertz. The power factor is 0.93 lagging, which is directional. Most all of what we're going to look at is going to be a lagging voltage rather than a leading voltage. And that's where we get those predictable power factors from. And then you add this all up, and the actual power is 164 kilowatts. So a little bit over 200 horse here. Also going to have analog gauges, which are doing the same thing. I would not suggest having a gen set without having some sort of dynamic gauges that are giving you feedback while it's running. It's just critical. And you can put you can have your electrical meters on it, and you can have your clamp meters and all that, and get all the same information. But it's so much more useful to get on with your day doing the other things. You can walk up and say, yep, I'm over 460, I'm good. Hertz, oh, that's a little low, I wonder what's going on with, is there something that's dragging on this on the system? Do I need to look at an open line, or do I have a motor that's going out? And then knowing what your amps are. Like that diagnostic becomes critical. Remember, all of this is going back to that point that you're the utility now. And the only one that's hurt by you not really monitoring what kind of power you're producing is you, because you're also the customer on the other side. Just like an electric motor, these gen sets are going to have their nameplate on it. There's a lot of good information on them, things you want to look for. Obviously, here's your kilowatts, the voltage, the amps, the hertz, and the RPMs. Other things you'd want to look at would be, make sure it's three-phase. And then your power factor, which in a lot is represented as cosine theta, but you're going to look for something that looks like a power factor. We had a big jump on that. We'll go back. Okay, just another example of an electric motor nameplate. Same things. So maintenance schedule and cost to consider. Top end overhaul on a gen set, probably 5 to 7 years. This is an industrial motor at 5,000 to 6,000, maybe a little bit more per major overhaul, 10 years plus. A lot of our industrial motors, if we take good care of them, they're going to last a long time. The generators will last a long time as well. So it'd probably be considered some sort of CapEx investment if you're doing this, depending on how you want it to line it out. Your major overhaul term is way out there. Oil change interval when you're really going, it's got to be something like once a month, and be thinking of 12 to 20 gallons of oil when you make that oil change. So price that out. Obviously, you want to include plugs and what other items go with that. Some things that are critical components to the system when you're using a gen set. The variable frequency drive and the soft starter become a very important non-optional tool for you on your submersibles. We often can get away with a pumping plant panel on submersibles just on because they're usually low load and the line can handle that. When it's a gen set, you don't want your gen set to handle that because it's not a big enough, robust enough generator. It's going to drag a little bit. It can't recover so quickly. So when you put all of, even if it's 15 horses, even if it's 50 horses, you put all of that horsepower online at once, it's going to drag down the motor until it can recover and catch back up with RPM. So you're going to want to use some strategy there to make sure that your start is a ramp, and if you can, that you would slowly ramp into it and avoid that peak, that inrush current. Variable frequency drives are a good tool. You probably are familiar with them now. 10 years ago, it was novel enough that this was a different discussion. Now they're pretty ubiquitous. I would be surprised, I'll ask, how many of you do not have a drive on your operation? Most everybody's got a variable frequency drive somewhere, okay? It's a good tool. I think even side-by-side horsepower per horsepower, this is how this industry has changed. You probably can get a less expensive drive in a panel than you can an equivalent soft starter in the panel. At least the retailers that I've been working with, drives are on the table up to 100 horsepower just ready to go, where the soft starts have to get ordered in. That's how the industry has changed in that way. May not be the same here. It's been a long time since I've priced the drive here. So here's what we're trying to accomplish. We're trying to avoid inrush current. Remember, you're thinking of this both ways now. Not only are you the operator, but you're the provider, you're the utility. And your gen set is your capital there. And so we look at this curve. If the motor was not running, it got turned on. Typically that first shot of electricity, by the math of it, it drives the current to infinity. Okay, just the way it works, because nothing's moving, there's nothing flowing. In an instant, that current level is trying to move to infinity because your volts have finally came online. At some point, the system catches up pretty rapidly, and you get a ramp that comes back down, and then you move to your steady state current. This shaded area under this inrush curve is basically burnt electricity. It's not contributing to your system, but it's also the place where you can cause major strain on your system. That's when you can blow out contactors. That's where you can overload and trip breakers because they're trying to protect your system from spikes. Oftentimes you can initiate a spike by turning on a motor that doesn't have some sort of starter or a controller. It's, as you know, the electric motor doesn't have a throttle that you can lean into it. It basically would be giving your pickup, your tractor, full horsepower from a dead stop all of a sudden you can imagine what happens there. You're going to start breaking drive shafts, busting gears, etc. That's what's essentially happening in this inrush scenario. But with a soft starter or a drive, you can defeat that by creating a ramp that goes from the zero start and getting to your steady state current once you need that steady state current. If you think of how you're pumping water, for example, you don't need the pump to spin really quick and generate all that horsepower because you've got a pool of water that you're lifting from. If you can apply enough energy to lift that water 1 foot, then 3 foot, then 10 foot, then 100 foot, you get that chance to ramp into that load. And so we need to take advantage of that by using a variable frequency drive or a soft start. And I would say with the genset in every application. I don't think there's an application where you're going to be beneficial to have an across-the-line starter there at all. It does come with some caution though. Since you're probably looking at submersibles, we'll go a little farther forward. Submersibles are built with a thrust bearing. Okay, a thrust bearing, it's a little bit like the regulators. You kind of have to set them. Okay, and if you don't start a submersible quickly enough, that thrust bearing won't get the water loop between it, and you can start to burn out the pump. And so there is a limit to how quickly or how slowly you can ramp a submersible. You need to be mindful that you can ramp it a little bit, but you're going to need to get that submersible to horsepower pretty quickly. If you've got a variable frequency drive on a vertical hollow shaft or a motor that's isolated from the pump, you can spool that up for a week if you wanted to, and it won't really make a difference. But with the submersible, you have to be cautious of this thrust bearing in it, so your ramp needs to be pretty quickly. And essentially, the recommendation from Franklin that was on the other page is you need to reach minimum flow in 2 seconds. Okay, so this is a little bit of a challenge here. It's like I don't want an inrush, so I need to start this thing slowly enough, but I need to get to my flow in time enough that I can functionally have a thrust bearing. And so you're working with some very sophisticated controls to say, here's my start, here's my full throw. I'm doing all of this within this weird 2-second window. So just a caution. Okay, the other considerations for this system, because now you're a lineman today as well. You have to size your electrical line. This is one thing I would recommend you either have your provider do or contact an engineer to help you with. It's pretty easy math, but you really don't want to mess it up. You want to get bigger wire size than necessary by a little bit, because the penalty of undersizing your wire is massive, but the cost expense of oversizing your wire makes it cost prohibitive. So you really want to line out what you're doing here. So you would want to take all of your load sizes combined. You need to calculate for your length of wire run, including all extensions, all the drops to each of the motors. You need to decide whether you want aluminum or copper. In every case, aluminum is a better, or excuse me, copper is a better conductor, and in every case, aluminum is substantially cheaper. And so you're going to weigh that. Also, don't know of scrappers who are really hauling much aluminum off on purpose. So you might be strategic on where you place the aluminum and copper. Then you'll need to look at your starter and motor controls to see what kind of energy you're burning off there. And then number 5, just an example, installed cost approximately $6 per foot for this 4/0 direct burial aluminum. That price has probably gone up in the last year, but that price has been pretty stable for a while. So if you compare that though to the 12-foot per run for the utility for 3-phase, there is a coupon to be clipped here by running your own wire. Most of what I'm talking about with wire, however, is going to be direct burial. So you're going to have to be mindful of that. You've now got something underground on your operation. I would not really recommend running most of this through the field unless you want to go really deep. It's not fun to be repairing an electrical line in the middle of a pivot if you, for any reason, had to till in that area. Good idea, since you know where that is when you install it, that you go ahead and mark it with some markers. That way everybody can know where it is when they're having to repair around it as well. So here's an example, multiple pumps on one generator. The idea here is this well currently has a 496 and a vertical hollow shaft, but the actual water produced can be done with 75 horsepower, where you've got 3x the horsepower out there. You don't need that much horsepower. Maybe 2x plus. Another one here, this is not so uncommon. You've got a well that used to need to have a 496, but now you've only got the water for a 25 horsepower sub. Same here, 496 and 20 horsepower sub. And then you've got a gen set in this area, and you've got a pumping plant there as well, something like 100 horse. But the idea is, can I add up my loads, keep it under the size of this gen set, bring natural gas to one, so instead of servicing with oil changes, spark plugs, starting up, shutting down, having to service all of these, can I go to one spot, make all my inputs, get this whole system up and running, and then only have to look to check and see if each one's running? That's the benefit of the gen set in these scenarios. Going back to this, you can see that there's a lot of lines. You've got to run a line here, a line here, and a line here. An example of that line loss calculation would be, what's your volts and amps at the gen set, go all the way out to the volts and amps at the submersible. You see you've had a little bit of a voltage drop, which is going to happen. The amps are pretty consistent because the amps are measure really the work that's getting done here. But you can calculate the difference between the available energy at the start and the available energy at the location, and you can figure out what type of power you're losing. In this case, this operation is going to lose 3.4 horsepower. So over the course of 24 hours, that 3.4 horsepower was worth $3.60 a day, or essentially a line loss privilege of $325 per year that you're going to pay in loss across that. You can size your line one size bigger and eliminate this almost completely, but those are the factors you have to weigh out. How many years is it going to take at $327 to pay for the next size larger line? Most cases you're going to get pretty close, make sure you've got enough capacity, and then go with it. Again, aluminum versus copper. This is an example of copper that I pulled out. It's subject quite aggressively to decay and corrosion in the ground, especially if the shielding gets pierced. The copper is usually a little bit better direct burial, but still not perfect. But oftentimes you want to look at a conduit. We'll show a conduit. Highly recommend stranded cores, something like this, where you've got a lot of stranded, bundled, all within. AC moves much, much better on thin, fine wire, so the more fine wires you can get going through it, the better you're going to convey that electricity. And here's an example on a sod operation where it was in conduits. I would never recommend doing a conduit like that, but I would recommend a conduit like this almost all the time for this application. A single shake injection conduit, one that you can actually deal with. You've got to lay the conduit and pull wire for a quarter of a mile. I mean, I'd be calling up the utility and saying, hey, can you bring me some power? Because that sounds awful. There's plenty of options if you want to do this more than once of how to do it right. This is a local rig. There's a couple local rigs around. If you're thinking pretty serious about it, I think I would probably try to contract out with someone to take care of injecting my line. Just don't want to mess it up, and it takes a long time. Trenching it with a backhoe, backfilling it, or even trenching it with a trencher and backfilling it is going to be much more onerous than using a vibratory plow or a plow that's specifically set up to do it, where it's got reels on the front, GPS guided, depth guided, etc. Plus you can get a map afterwards of where it's installed that you can keep for your records. So some operational procedures. We've talked about putting it in. Running it's got its own set of parameters as well. There are some simple things, but they're useful and necessary. One, you want to start the genset motor without a load and allow it to throttle up to some degree. This is a little bit of a challenge. If you notice this genset, for example, it's got a cooling coil. Okay? So you don't get a lot of time to get that thing up to speed before you got to start pumping water. Most cases, I would say probably consider a bit of a radiator if you're looking at a gen set rather than cooling coils. It's a little bit of a trade-off, but it allows you to get things up to speed. It also allows you, in case this well goes down, the opportunity to run your other wells while this one's out. In this particular one, if one well goes down, 5 wells go down. Because you can't pump this without the radiator. The next one, after you've got the motor running and you're happy with it, you engage the generator breaker to energize the electrical system. Still with no load on the gen set, if you can help it. So the way that you would do this often is you have disconnects at the gen set for each one of your satellite wells. They'd all be in the off position. You'd turn them all on at that point when you're going, but you'd start with them all off. You start one load at a time, starting with the largest load. Ideally, the largest load will be the closest one to the gen set. If you're thinking about it, that means less cable to take the power there, but also it's going to be the one that you're going to want to run most often. So sometimes if you're only running one, it'd be the one right by the gen set. Then you're going to want to do what we talked about to minimize the inrush currents. You have a VFD or a soft start, one at a time, get up to speed. The next one, get up to speed. Next one, and get up to speed until the whole system is operating. And just to reiterate, if you can, placing starter controls near the gen set will make your life much easier. That way it's one stop to get the whole program running instead of chasing the lap. Because that's one of the things that you get the chance to avoid here is chasing site to site to get them up and running. The shutdown process, ideally you would do it in reverse. You'd remove the loads one at a time, and you could do it simply by disengaging the main breaker. And then my preference, just being a fan of mechanical systems, let the oil reach an equilibrium temperature, let it idle back a little bit, and then shut it off. The maintenance schedule, just reiterate here, oil change monthly, plan on that, oil or air cleaner is needed. If you can help it, and this is not usually a problem for us for about 90 days of the year, don't shut down frequently. The hardest part of it is getting it up and running or shutting it down. If you can get it to that equilibrium state just where it's running, that's where the gen set really works for you. That way you can go do the rest of your work that's going to actually, in my mind, make you money. I still think of pumping plants as valuable as they are as a cost and effort center. It's a necessary part of farming, but if you can get to the point of what really makes me money farming, I'd much rather have you guys in the field. That's where your decisions that make you the most money are. One cautionary point regarding setting up the starter controls near the gen set. Do not omit this one major safety factor. You must have a kill switch or disconnect at each well. It can be simple. It can be just a simple on-off, but you must have one. In many codes, you have that within eyesight. I think you can get away with that where you don't have to. My must-have non-negotiable is that you don't want that power out there where something can go haywire and not be able to just hit that switch, take a breath, and save your life or not risk the life of somebody who works for you. We're still running 3-phase power to these satellites. Not being able to control that power out there is a recipe for disaster. Thinking of water combined with electricity and being in isolation, just put a disconnect out by each of those satellites. Like we said, locate the system gen set at the largest well. This would be one where I'd pay really good attention to cooling coils. The VFD on the gen set system gives maximized results from the gen set. One thing that I noticed once we started running VFDs on gen sets compared to grid power is on the lower horsepower submersibles, the contacts come in much more solid. I was testing a lot of submersibles for a while in that 3 to 30 horse range, and the starters were always buzzing, just buzzing. They were off phase. Okay, so I think I measured some that power factors were in the 70s. That's just kind of bad power. You cure that with the gen set. Also the VFD at those locations allows you to receive this bad power. And because there's a bridge disconnect in modern VFDs, it takes this bad power in, essentially disconnects it, and then realigns that power to something that's useful on the other side. And so what you end up with is much better control of your motors on the other side. Much longer lifespan of those components as well. We found that a VFD allowed us on this particular one, which is the case study here, the VFDs on those satellites allowed us to take this genset up to 100% of its service factor. You could run full capacity all year long, and we think the VFDs were a major part of that for a number of reasons. If you're going to automate a VFD based on a pressure transducer to balance your system out, and this is good practice anywhere you're using drives, VFD on only one well. If you don't, you create this hysteresis where these VFDs start making corrections and they fight each other. And they will go into almost an infinite loop, and they will get farther and farther off from equilibrium the longer you go. So be strategic, place a VFD on only one of the wells, or what I mean is an automated VFD on only well. Use drives on all of them, but an automated one on only one. Again, utilize soft starters in addition to, or not in addition to, but in place of VFDs if you'd like to. Just avoid the across the line starters. Reiterating that. Here's a good one too. If you're going to set up remote start vertical hollow shaft wells, go ahead and invest a couple $100 in an automatic oiler. And my favorite for an automatic oiler would be a 2-oil dripper, one that's got a solenoid on it that triggers on when it comes on, and the other one that's dropping at a very slow rate. So this one that's manual, it can drip something like every 30 seconds or maybe even once a minute. Your automatic one, when it kicks on, that's the one that's going to give you your drip based on your well depth. So something like every 3 seconds or 5 seconds. The idea behind that is the vertical hollow shaft, as deep as the pump is, every 5 feet there's a bronze bushing. The tolerances are a lot closer than you'd like to think. You want to make sure that it's well oiled. If you're going to remotely start and you want to make sure that they're not running for that number of minutes until you can get over there and turn the dripper on, you'd rather have that dripper going at full bore right away. Then you can get over later and make your adjustment, but at least you know it's going to have oil from moment one. All right. What kind of time we got, Steve? We got a little time left?
Yeah, you got about 12 minutes.
Awesome. Let's put the other one back up. You got any questions on gensets while we're covering that ground? I think it's a useful part of our tool bag. I just don't think it's the ubiquitous one that maybe for a while we thought it could be. I also think there's people that have gotten a lot of experiences where when we first started presenting on gensets, it was kind of scary and intimidating. You guys don't seem very intimidated about it, which is awesome. I mean, we've closed the gap on that a little bit. That knowledge transfer's coming.
The only reason we started running the Jensen is because we had the motors. And it was just cheaper to get it set up than to use just regular.
Yeah. You still happy with that choice?
For now, we are.
Yeah.
Yeah.
I think it's a great choice in that scenario. They've got the capital already. Good.
Are you running belts on your generator?
You what?
Are you running belts? Because
Some of them.
I found just this year that a belt can look good and it'll get everything vibrating,
Yep.
and you need to change it. Usually you can see it cracking, it's
Yeah, you can tell it when you run them a while and kind of figure out.
Do you remember which one?
Pretty quickly, like that,
Mhm.
like that.
Another thing is to balance your hands.
Yeah.
Nick, you were talking about that double dripper. Is that pretty common, or are there some specific brands?
I've only ever fabricated them,
Okay.
but it's pretty simple. It's like a red dot solenoid. That's the only thing. Everything else just looks like a normal dripper.
Okay. Yeah, I thought you were talking about a fusion tank.
There probably is one, but I don't know of one. But I would highly recommend manufacturing your own. It's Let's go a little farther, Bailey. Let's see. A little more. We're about there. Oh.
When the drive has power, the sun
They're not without problems.
Say it again.
They're not without problems sometimes, though.
Oh man, drippers are definitely a problem.
Well,
Bailey, let's go up to like slide 80.
Drippers are, the Jen said in general, they've had some problems with motors.
Yeah.
You know, just problems that they really didn't foresee, but it was very real.
Yeah. We're gonna jump back into some of these things just so that you make sure you get your money's worth there. Speaking of different and alternative fuels, I think we talked about dual fuel back here, diesel. Then we talked about trading out and getting horsepower balanced out. This was one, going to that point of making sure we had enough volts. Then I guess a nice fit, our on-site electricity generation. That was a great project. We went and highlighted that in our last 30 or 40 minutes. On occasion, things come up too for pumping that are interesting. This was one that was hydrogen generation. I'd done 2 efforts with Brown's gas generation, trying to test them out. Neither of them worked. So occasionally you'll see the strategy of, hey, we're going to generate hydrogen, and we're going to fuel hydrogen through this. It's going to save all the world in emissions and power and free energy. Those are the type of things that I would like to caution everybody to be a little bit narrow-minded on those claims, because most of these things, if they haven't made it to market already, they're not really useful. So this was a diesel pumping plant. This is literally an Eder, like walking distance from here, where we did this on like 4 or 5 motors. And it was a great strategy, great idea, but consistently what we found is this Brown's gas generator. So let me take a step back. This is my pumping plant evaluation setup. So I've got a torque cell here, so I can measure the horsepower generated by the motor and going to the gear head. Then I've got flow meters, so I can measure the water coming out, pressure gauges, so I can figure that out with the water horsepower calculation. I've got a diesel fuel meter, so I can measure the diesel that was going into here, so I can measure input energy, output energy, input energy, and output energy. You can really tease out at what point in the system is strong, which is robust, and which is inefficient. So in this case, what I can find on each of these wells, and you're going to laugh, I can find quite literally a slight change in horsepower when we run the Brown's gas. And I thought, I'm not quite getting why this is, but in almost every case, I could go back then and measure the voltage draw off of these batteries that was driving this Brown's gas generator, and it matched the incremental increase in horsepower. So we were getting a basic break even in energy here, but it wasn't changing much of anything over here. So I would just be cautious. That's why we talk kind of carefully about the fuels that we use. There's not really a silver bullet unless we start talking nuclear. You want to talk something nuclear, I'm all in. Portable nuclear on these would be better than any of them. You remember earlier I mentioned I want to get to common denominators. I want to get to a common language. And we talked about dollars. The quicker I can get to dollars, the more everything can talk to each other. In these systems, the pressure equivalent is the equivalent of that. So the thought to burn in your mind, 1 psi is 2.31 feet of elevation. We've now seen it a couple of times. That idea is that as you go uphill, you're going to get some pressure accumulated. Well, you could take a lateral system too. You could take friction in a pipeline system. You can also relate that back now to elevation or PSI. So what this allows us to do is combine and evaluate friction losses from things like pipe sizes, fittings, elevation losses from changes, pumping depths, etc., and pressure losses from things like choke valves, nozzle packages, etc. Put it into the same system, and then see where you can make an economic change in your operating system. This is where this makes sense, and this is the busiest chart on here. If you do want to figure it out, I encourage you to look at your book. This is one of these things, however, that will change your irrigation system economics immediately. Okay, the idea being that if I've got the pressure at my pumping plant on the bottom and a percent change for every 1 change in PSI, I can now tell what every last incremental change in my system is in terms of percent change in dollars. You can relate it to dollars right away. So the idea would be if this is your pumping depth, from 100 feet, 200 feet, 300 feet, etc., and your pumping pressure from 15, 20, 25, etc., you would look from this pressure and where you're pumping from, and there's some overlap or some index point on there. Where you can say I'm pumping at 20 psi and I'm pumping from 200 feet. What I can see is roughly every single change in pressure is worth a 1% change in my pumping cost. Okay? Remind you, this is busy and nerve-wracking to get your head around this. But the example is if you do something that's worth 20 psi, in this scenario, that's a 20% change in your pumping cost. So if you want to impact your bottom line by reducing your pressure losses away or your system losses along the way, this is a way that you can tell how impactful this could be. The scenario looks something like this. So let's use a pipeline example. So you've got 700 gallons per minute that you want to send down 1,000 feet of pipeline. If you want to size that pipe, you would look at a 10-inch pipe, an 8-inch pipe, and a 6-inch pipe. You've got flow velocity, where the standard is in these water systems less than 5 feet per second. So we've now got two pipe sizes that match. We've got a 10-inch and an 8-inch. The 6-inch is just too small for the 700 gallon per minute. The water's moving too fast. Add up the friction, or look at the friction head losses from that. You can see if I go with the 8-inch, it's going to be 9 feet of friction loss. If I go to the 10-inch, it's much more subdued. And if I do the pressure equivalent, it's the equivalent to 4 psi versus 1.3 psi of loss. In this case, the major difference is between the 6 and the 8. So you definitely don't want to go with the 6, but you would have to really do a little bit of strategy to see, do I want the 10-inch, do I want the 8-inch in this scenario? In most cases, the economics, if you are looking at it on a 5-year horizon or less, is I want this 8-inch. If you're looking at it on a permanent horizon, you think this is my property for 40 years, I'm going to do it right the first time, you would go with the bigger pipe. Another example would be when you're fitting these pipes. This is a picture actually from this station, this water conservation center, where it's an 8-inch pipe. The builder says, I'm going to build me an 8-inch saddle. We'll see what he did in the middle here. If you're a fabricator, you're like, oh, that's way better. Like, I'm a lot stronger. If you're paying for the energy on that, though, that basically takes it from an 8-inch pipe to a 6-inch orifice, and that comes with a huge pressure loss. In this case, it's a 4 psi loss for every drop of water that flows through that. Okay, so what he did in this case is basically that single joint was a 4% increase in the pumping costs in perpetuity. And if there's 10 of those joints, they accumulate. Okay, so you're making these marginal changes here. This is my caution to say, don't be fast and loose with just slapping stuff together, because you'll have to pay for it on the back end with your energy costs. The variable frequency drive has made these choke valves go out of vogue, maybe thank goodness. Who has seen a choke valve like this where you've got 90 psi on this side so that you're not...
Got a bunch of them.
I know, but they're expensive. Like, this is a huge input on the pumping costs. It's a necessary evil, but I'd try to make it as less evil as possible if you can, by doing things like adding a drive to those in the cases where it fits. Other ones would be matching your pump curve to your available water, not in April, but in August. I'm going to walk through this pump curve and we'll be done there. This might address a little bit of your question earlier. Okay, so this pumping curve is the heart of your system. It's the contact point with the source of the water in the aquifer. You've got to get your pump right. That's just the way it is. So to get your orientation on this pump curve, you're looking at capacity in gallons, and then you'd have horsepower for this chart, and then you would have the head developed per stage on this chart, and then this number up here is referred to as your net positive suction head, which means how much water you need to have above the inlet of the pump. Okay, so 0 to 10. You can see that as the flow goes up, you need to have more feet above the pump. As the flow's down, you don't need so much, etc. Then what you've got in the middle here are these efficiency curves. Okay, so in this case, like an 82% efficiency and 81% efficiency, this loop would basically be the 80%, 78, 76, 74, etc. So the question you'd had earlier is, why do I see some pumps where one has me 86% efficient and the other one has me 82% efficient, but then I come out here to the horsepower side and it's calling for more horsepower on the one that's doing less work? I can't answer that completely for you. Most of those pumps are set up in test pits to characterize them, and what they publish is the characters. And different manufacturers do different things. Some bowls are a really heavy bowl, and the parasitic load of turning a big shaft is going to be more so than others. So I can't speak to yours on particular, but this is where I would go to find it out and look at that.
American Turbine makes a check valve in the top of that bowl. And if your motor dies, you can start it. And it lets that water slowly trickle down, and sometimes you don't pump sand anymore from the gush. They're going down. Start them up slow, you shut them off fast you want to.
There's different strategies on shutting those wells down. Like if you got your vertical hollow shaft, oftentimes you'll have some catch dogs in the top of the motor, and so that ratchet will hit, the pump will stop kind of violently, and the water will flow straight through it. What that can do is it can force out and through the aquifer. In many cases, I see that kind of beneficial because it's doing some development work on that well. It's pushing some of the sand back out of the gravel pack. But in some cases, you don't want that. And some strategies will have the well specifically even backspin. Do you know why they would have the well backspin?
Open up formation.
The backspin's interesting because the pump will pump in reverse.
Correct.
If you start spinning it backwards, that water kind of fights itself or it doesn't know whether it wants to fall or rise, and so the water actually flows through it quite a bit faster when the pump's
If it don't spin backwards, water goes down faster.
Yep, that's right.
Jerry Thompson over here at Dumas is the one that designed that check valve.
It's a good strategy.
It works.
You know, most of the submersibles have those check pins and check valves.
Yes.
Are you talking about one that still can shut it down while the head's in place? Or are you talking about one where you have to break them off?
No.
Like for
whenever
repair?
You quit asking for water, that's just a gravity check valve.
Yep, very good.
And barely leaks back.